Okay, here we're going to look at trigonometric modelling. So practical questions involving a lot of the trig work we've done so far this year, mainly graphical work, but a few other bits and pieces as well, solving trig equations, etc. So let's go on to this first question without further ado. Whilst out in his trawler, John North, a fisherman, notes that the height of the tide in the harbour can be found by using the equation. He's quite smart, John North, to see this equation. Anyway. H equals 5 plus 2 cos pi on 6t, where h is the height in metres of the tide and t is the number of hours after midnight. What is the height of the tide and when does it occur in the first 24 hours? So we've got a equation here for the tide, and it is h equals 5 plus 2 cos pi on 6t. What is the height of the tide? High tide. So high tide is we're looking at maximum. And we mentioned earlier in the year about how we can look at this, and that any cosine value, regardless of what's after the cos bit, any cosine value is always maxing out at positive 1, and minus 1 is the minimum. Now, do be careful here, because here we're looking for where this value there, that value there is equaling 1. Now, we can do that because we've got a plus there. And if it equals 1, the cos expression, we're going to get maximum height. If that was a negative in there, just be careful, the 1 would give us minimum height. Just need to be careful of that one. But anyway, the highest value, what I've got in the orange triangle there, for that cos expression is 1. Okay, so the highest value the tide can be is h equals 5 plus 2 times 1 equals 7. So 7 metres is the answer. Now, when does it occur? Okay, well, it's going to occur when cos pi on 6t equals 1. Okay, that's where it's going to occur. So what values have a cosine of 1? That's the question we have to ask. If we look at our table on page 300, we know that the cos values here that give 1 are 0, and then also 2 pi after that, and then 4 pi after that, etc. So the first time it's going to occur is when pi on 6t equals 0. So we need to solve that little equation there. So pi on 6t equals 0. Okay, multiply 0 by 6, we get pi t equals 0. T equals 0 divided by pi. T equals 0, and because we know that t is a number of hours after midnight, so that little statement there, because we know that, then if it's 0 hours after midnight, then the time when the high tide first occurs, when t equals 0, that is actually midnight. So there's our answer to question A. Question B asks us for the difference in height between high and low tides. So here's our equation, and I've forgotten my h here. H equals 5 plus 2 cos pi on 6t. Now I've already worked out that maximum height equals 7 metres in the previous question. Now minimum height. Well, minimum height's going to occur when that expression there equals negative 1, because remember, and we looked at our cosine graph now, that cosine and sine graphs have a maximum at 1 and a minimum at negative 1. So the lowest value for that cos expression is going to be negative 1. So in that case, height will be 5 plus 2 times negative 1. Height equals 3 metres will be the lowest. So the difference between those two, between high and low tide, will be 7 minus 3 equals 4 metres. Question C now asks us to sketch a graph for this equation, h equals 0 to 24. Now I've created a graph here using the Desmos program, but you could also put this graph into your calculator as well. Set your axes, very important, from over here at 0, okay, over there, through to 24 over there. And we know that our graph is going to go between, our graph's going to go between 7 being the highest and 3 being the lowest. So I've got a nicely spaced out graph there because I've got plenty of room. Now I'd stop at 7. I have the bit of room above 7 there, and a little bit of room below 3 there. And also I've got the graph set at between 0 and 24. In fact, if you look carefully, I've gone from -1 to 24, just so we can see the whole graph fairly easily. So that's the graph of this equation. And the equation, of course, is h equals 5 plus 2 cos pi on 6t. So that's the graph of graph there. And you can see we've got high tides and low tides. So the first high tide there is at midnight. Next high tide there is at noon. Okay, so 12 hours past midnight, which is noon. And next high tide is back at midnight again. Low tides, we've got 6 AM and we've got 6 PM as well. So we can quite clearly see where our low tides are there. Here's the same graph now recorded on our TI and SPI calculator. Notice set it there between 0 and between 24. And once again I've got, I think I set this one at 8 maximum and 0 maximums. But anyway, you can see the graph quite clearly there. Once again, although the TI and SPI won't label your axes, it's not hard to work out that that's 6 there, and that's 12 over here. Sorry, not 12, that's 18 over there, 6 PM, beg your pardon. There, so, and 12 in the middle there. So you quite clearly see what the marks are on the axis. So there's two ways of graphing it on the Desmos program that I've showed you. Entry of your equations quite crucial here, that you've set it out correctly. Make sure you can do that. If you have troubles with that, please see me. Of course, I've used, instead of T there, doesn't really matter. Well, it does if you're in a graphing program. It's just as easy to use X there. Alright, now question D we're up to. And this is sort of an exam classic, this one. John North knows that his trawler needs a depth of 6 metres to enter the harbour. Between what hours is he able to bring the boat back to the harbour? Alright, now a few ways of doing this, but since you've had to graph it already, the simplest way is to graph a second line. And the second line of graph here is an F2x, and I've just simply graphed 6. Okay, and if I graph 6, that gives me a horizontal line, and it intersects in various places with my original equation. And you can quite clearly see here that the tide is going up and down, so up and down like that, and at certain times it's above 6. Okay, so at certain times it's above 6 there, and there, and in there. And what you can do then is you can find those points of intersection. Okay, we've done that before this year. Once again, if you have trouble doing that, please see me about it. But if we find those points of intersection, there's 4 of them, there, there, and there. That tells us when the tide is above the 6 metres. That's when John North is safe. Okay, let's look at those times then. So it's above 6 metres. Let's take this first section here. If we take that first section there, it's above 6 metres between first section between midnight and 2 AM. It's also in this section here between 10 AM to 2 PM. And the third little bit over here, which is 10 p.m. to midnight. So if we took it all of that, it's a total of 2 hours there, 4 hours there, 2 hours there. That's 8 hours in total. It's above 6 metres. Next question. On a summer's day, the hourly temperature, which can be approximated to a cosine curve, was recorded. The maximum temperature was 30 degrees and occurred at 3 p.m. The minimum temperature was 10 degrees and occurred at 3 a.m. The temperature was first recorded at 12 midnight and every hour for 24 hours. What is the amplitude of the function? I'm just doing a quick sketch of this situation. I've got time here, 0 to 24 hours. And I've got temperature on my y-axis. And we're told that at 3 a.m. we've got a minimum. Okay. And at 3 p.m., so that's 15 hours, we've got a maximum there. Okay, so we're going to have a curve here that's going to look something like this. Okay, and down again. So that's sort of what we're dealing with here. And it's asking us for the amplitude of the function. Now, the amplitude is half the distance, remember, between the minimum and the maximum. So our distance here between minimum and maximum, if we look at that distance there, okay, that's going to be 20 degrees. So our amplitude, our answer for A, is going to be 10. Okay, it's half the distance between the minimum and the maximum, so that's our amplitude. What's the period of the function? Right, so we need a distance here for one full wave. Well, if we extend this graph a little bit, it's going to keep on going there, and it's going to go down to there. So pretty much the full wave, okay, is 24 hours. So our period is actually 24. The middle value of the function, so we need to look at our maximum is 30, our minimum is 10. So the middle value of the function, answer to C, is going to be 20. How far has the middle value been translated up the y-axis? Okay, so if our middle value, and I might just put it in here as a dotted line, if our middle value there is 20, okay, that means the graph, the original middle value of the graph before it was translated upwards would be, of course, down on the axis here. So it's been shifted up 20 places. So D, how far has the middle value been translated up the x-axis? Because the normal middle value is the x-axis itself. Okay, so that's y equals 0. It's been translated up 20 spots there. When do the maximum and minimum temperatures occur? Well, we're actually told that in the question, which is a strange question. So when do the maximum and minimum temperatures occur? So fairly easy, we just have to read the question for that one. It's going to be 3 a.m, which I've got directly from here. I'll use my little triangle there. At 3 a.m. is the minimum, and the maximum is at 3 p.m. Strange question that, because they don't really have to work it out. It's actually in the question. So 3 a.m, 3 p.m. for minimum and maximum. And last question is we have to find a equation to model this function. Okay, so let's have a look at that. Alright, this is the big part of this question. This one's worth the most marks in exams. This part F here. Using all the above, write the equation to model the function. So let's have a look. Now, what I've got to do is bring this graph to the axis, because if I bring the graph to the axis, I create a cosine function. Now, I can either do it two ways. I can bring the graph a little bit that way. Sorry. A little bit that way, and I've got a cosine function, but it's a negative one. I can do that. Or I could take that point there and bring it to the axis, okay, and make it a positive cosine function. A couple ways there. And there's actually another couple ways after that. There's lots of answers here. If you look at the back of the book, it gives quite a range of answers. To me, I want to bring it, when I do these, I want to bring it the shortest distance. So I'm going to go for that first option, which is to bring the graph over to here. Now I've copied this graph, and I'll see if this works. And I've copied the graph, so I'm actually going to bring it over to there. like so. As you can see there, for some reason it's rubbed it out a bit, but I've moved the original curve over to the left. Now, how many places is the question? How many places have I moved it to the left to create that graph? All right, that's the left-right shift. But there's another few things we need to know here. So, first of all, the amplitude is 10, and it's upside down. So my equation is going to be y equals upside down, so negative 10. Oh, sorry, negative. It's 10 because that's the amplitude. Cosine. Okay, the period is 20. Sorry, not the period. It's been shifted up 20 places. We'll get to that in a minute. Now, we have to look at what the period of this graph is, because that's pretty important. So I'll just pause there for the moment. Period equals 2 pi over n. The period of this graph, one full wave, was 24. So 24 equals 2 pi over n. Continuing over here. Swap places, n equals 2 pi over 24. N equals pi on 12. So next to the cosine here, my period is pi on 12. Now my left-right shift. Okay, back over here. What did I have to move the graph by? To the left, to take it to the axis. Remembering that the graph had a minimum there at 3. Okay, it had a minimum at 3. So what I could do was take that graph 3 places. The graph has been taken to create it on the axis. It had to go to the left. But from the original graph, right, this is where it gets a bit mind-bending. To create the graph that I've got, I actually had to take the original graph and move it 3 places to the right. So what I'm imagining now is I had this original graph that was on the axis, not shifted anywhere. What did I have to do to create the graph I've got now? I had to shift it 3 places to the right. Therefore, in here, okay, I have a minus 3. Then I look at my translation, 20 places up. All right, let's digest all that, maybe on the next slide. So let's copy that over. Actually, we've got a couple of questions to get to yet, but I'll just take this over. And here it is. Let's go through it bit by bit. Change pen colour. Negative. Why is it negative? Because the graph is the cosine shape, but it's starting down here at negative 1. 10. Why is it 10? The amplitude is 10. How did I get that pi on 12 there? The number next to the cosine on the right of it, okay, either before the x or before the bracket, is the period. Period equals 2 pi over n. Okay, and I used that formula to work out, and I knew the period was 24, without doing it all over again. I used that to work out n. Right, why is it minus 3? Because to create that graph that I've got now, that one, I had to take the original graph that was on the axis and move it 3 places to the right. Why is it plus 20? Because the graph was shifted. The middle line there in that graph, blue dotted line that's still there, was shifted up 20 places from the axis. So there you go, there's one possible answer for that question. Let's move on now quickly to G and H. Check the accuracy of your work by using your equation to find the temperature after 3, 9, 15 and 21 hours. I'm actually not going to do this because the video is getting quite long there now. But what will you do now? In fact, what I should do here, I'm going to actually fix this up a little bit better. I'm going to replace y with t. I'm actually going to take that 20 because it looks a bit better and put it out the front. Minus 10 cosine pi on 12. Instead of x, I'm going to use little t for time, minus 3. And that's a better way to put the equation. Okay. Now, you can try it yourself. This is question 6G number 7. Please try yourself G and H. But what you do there to find the temperature after 3, 9, 15 and 21 hours is you'd place those values in there for t. And then use your calculator, or you could use another method if you could use Trig quite well to work that out as well. In fact, I might what I might do, having said I was going to finish, I might just work out one of these, not all of them. That might be a good idea. Just copy that to the next slide. Okay, let's get rid of that there. So let's use that equation, for example, to find. So we're going to find T, temperature, when T equals 9. So that's one of the questions we were asked there. So if we sub it in, we get T equals 20 minus 10 cosine pi on 12 outside of 9 minus 3, which is 6. Now, the more I look at this, the more I'm thinking, yes, this could be a non-calculator question, so I'm glad we're doing this. Pi on 12 times 6, that's going to be 6 pi on 12, which is going to be pi on 2. Okay, so it's cosine pi on 2. Cosine pi on 2 is 0. Okay, so we're going to get T equals 20 minus 10 times 0. T equals 10 degrees. Sorry, no, it's not. That's wrong. 20 minus 0 is 20. What am I thinking? So that answer is that actually 20 degrees for that one. Sorry about that. Okay, so might be an exercise now for you to do the same process. If we go back to the question, I've done this one here, 9, but you can try it with 3, 15 and 21 and see how you go. All right, that's a bit of introduction to trigonometric modelling. You can now have a go at exercise 6G. See how you go with that.